Thank you, Chairman Sir, and thanks to the organizer for inviting me for this conference. So today I'm going to talk about a relatively new phenomena, namely the orbital Hall effect, which has really gathered momentum in the last 6 to 7 years. And so this is an experimental talk. So the work has been done by my students here, written here, and all the work is done at the in-house facilities of IISER Kolkata. It's nice to have Professor Dattagupta in the front seat. He was our founder director, and many of the facilities were initiated during his time. So let me get started. So some portion of the work is already published and some is in the archive, and of course I will have new data to show you which is not yet archived or published. So the basic phenomena that I want to talk about is the transverse filtering of electronic angular momentum. So way back when Hall was working on Hall effect on different materials, he found that ferromagnets had a completely different response, and there was no explanation at that time, so he named it anomalous Hall effect. And so this is a typical graph experimental data that you can see here. So you see a knee-like structure, and the knee happens at the saturation when the magnetization of the film saturates perpendicular to the flow of the current. Now, to explain this, so it was a very hotly debated subject for several decades. So what is the origin of this thing? And it turns out it can be explained with the help of relativity, something called spin-orbit coupling. So to understand this, so spin-orbit coupling has many forms. So this is the form that helps you understand why this kind of extra voltage appears. So let me remind you, so the normal Hall effect, typically the slope is like this. If you take a typical metal, this is the slope, but you have a very steep slope because of the magnetization. So why is it coming? So what spin-orbit coupling, if you look at it this way, so the idea is a moving electron, it will see an electric field also as a magnetic field. In the rest frame of the electron, the electric field, there is an effective magnetic field, and the spin of the electron, which is the sigma vector, will couple with the magnetic field through the usual Zeeman interaction. So now imagine that there are two electrons, they are moving in the same direction, P, which is the current, but they have different opposite spins. So because of this term, we will see that the upspin will go in one direction, the downspin will go in the other direction, the transverse, of course transverse to the current. So what happens in a ferromagnet, the Fermi level itself, there is imbalance of spin. There are more upspin than say downspin. So as a result of which there will be a net charge accumulation which is different on the up and the down surface. So if you connect a voltmeter, you will measure a voltage, and that voltage is proportional to the magnetization. Now this simple physics can also be extended to a normal metal. So normal metal has equal number of an up and down spin. But the problem is, so now since you have equal number of an up and down spin, if you connect a voltmeter, there is no voltage. So even though this effect, which is called the spin Hall effect, was predicted way back in the 1950s, since there was no connection to any experiment at that time, it did not gather any momentum. Later on, in around 2000, people started talking about experiments on how to detect it. So I will show you. So this is the first major paper, the very famous paper by the Ashwalam group, where they actually demonstrated spin Hall effect. So what you see here is a Kerr microscopy image of a gallium arsenide sample at low temperatures. Current is flowing through it. So what you see here is the red and blue band. It represents the spin accumulation. So very briefly, what Kerr effect does is that when a polarized light falls on the surface, and if there is a net magnetization or spin polarization, the polarizer will rotate. The polarization of the reflected light will rotate. So if you have opposite spins, they will rotate in opposite direction, and they have measured it. So this is a very difficult experiment, and so that was the very first demonstration that indeed spin Hall effect existed. Now, my talk is about orbital Hall effect, So you can say that analogous to the spin, which is an angular momentum, block electrons also has orbital angular momentum. Okay, so if a current flows through it, the orbital angular momentum can also separate, and opposite directions, opposite polarization of the angular momentum will separate in opposite direction. But of course, this is a very simplistic picture. The actual origin of this I will talk about later is more complex. But the end result is that in an orbital Hall effect, you have accumulation of orbital momentum of opposite signs. Just like in a spin Hall effect, you have spin angular momentum getting accumulated at the edges. So now one of the debate about the origin of all this effect is whether this is intrinsic or extrinsic. So what do I mean by that? Extrinsic means that it comes from impurity scattering or defects. Okay, so this E could be an impurity potential. So whenever an electron experiences that potential, it will deflect depending on its spin orientation. But there is also a competing theory, which is the intrinsic effect, which talks about Berry curvature. So theoretically, people have calculated spin Berry curvature in material. So this is the important part. So spin Hall effect is true only when your spin orbit Hamiltonian is strong. So this happens only in so-called heavy metals like tungsten or platinum, whose atomic number is very high. So people have calculated this spin Berry curvature, and they have shown that indeed you can have spin Hall effect even in the absence of any impurities in a perfect crystal. So that was for spin Hall effect. So the question, of course, we'll talk about it, what happens in orbital Hall effect. But let me now proceed. So first of all, why do we even care about a phenomena where there is no measurable voltage? That is the question one can ask. So what is interesting about it? So the interesting thing is, the electronic control of magnetization. So that is something that we want to achieve. So let me walk you through this cartoon here. So suppose this is a magnetization, a small amount of magnetic moment M. And you somehow artificially you generate a spin polarized current, meaning that all the electrons, they are polarized in a particular direction. So what happens when such a current goes through this ferromagnet? So as soon as the electron enters the ferromagnet, it will experience a strong exchange field and it will start precessing. As it goes along, it will start precessing. And it will come out with some phase which is different from this. Now if you have a bunch of such electrons, so they are, of course, you have to think in terms of quantum mechanics, so they will follow different quantum mechanical paths. So the phase of all these electrons will not necessarily be the same. What will be same is the component of the spin which is parallel to the magnetization. The component which is perpendicular, it will be random for all of them. So if you add them all up, what you end up on the other side is a spin current which on an average is polarized along the magnetization direction. So the question is, what happens to the angular momentum which is transverse to the magnetization? So the answer is the ferromagnet absorbs it. And as soon as it absorbs it, it will undergo a torque. It will move. So this is the idea that if you have a spin current incident on a ferromagnet, you can induce magnetization dynamics without using any magnetic field. So as if the spin current behaves like an effective magnetic field. And this thing was theoretically worked out not long back in 1996 by Slonzowski. And in addition to these two terms that Shushmita, our previous speaker, talked about, where you have so you have two additional terms that arises only from the spin current, and it has the following form. So the form which is M cross sigma is similar to this M cross H, so we call it the field like torque. And the component which is M cross sigma, we call it the damp like torque, because analogous to Gilbert damping. So the idea is that, for example, if you have a spin valve like structure, F1 a normal metal, F2, like two ferromagnets separated by normal metal. So this is the standard GMR effect. you go from high resistance to low resistance state using an external magnetic field, but you can achieve the same thing using a current. So depending on which way you flow the current through your spin valve, you can actually flip the magnetization and you can achieve 0 and 1 state. So this has been experimentally demonstrated, but these are extremely difficult experiments because you need really nano pillars, you need to generate large spin current density and things like that, but these are all done. So that is the idea that why we want to study this kind of phenomena. So now it turns out that flipping of a magnetization is an extreme case, but in general you can actually track the magnetization dynamics even if you don't go to nanopillar, and it turns out that a simple Hall structure allows you to track those phenomena. So what happens here is that this is again a very simple cartoon. So what you need is a ferromagnetic layer and a non-magnetic layer, a bilayer structure. So the ferromagnet is your probe. The ferromagnet will probe what the spin current is doing, and the normal metal is the generator of the spin current. So both things are incorporated here. So when you pass a current, the current will get distributed through both the layers. So the normal metal will generate a transverse angular momentum current that will be incident on the ferromagnet, and there will be dynamics. So the combination of the two effects will give you a second harmonic voltage. So you pass an AC current with omega, and using a lock-in amplifier you measure the voltage at 2 omega, and you get a characteristic signal, and this has been phenomenologically modeled by Afki et al. Long back in 2014, and these are some typical graphs here.
How thick are these layers?
These layers are around 10 nanometers. Okay, and the thickness is also important, I will tell you. So again, this is a paper that we had published on spin Hall effect using tungsten materials. I am not going into details today because I really want to get into orbital Hall effect. And of course, we also calculate a figure of merit, how efficient my device is. So we actually calculate torque efficiency per unit electric field so that we can compare various materials. So the idea here again is, this is a schematic of the experiment. What we need is a vector magnet. So what we do is we rotate the magnetization in plane using a magnetic. So we have two poles and you can program them in such a way that you can rotate the magnetic field in plane, and you measure this 2 omega signal as a function of phi, which is the angle between the magnetization and the current. So that's all we do. That's the experiment. And there are various spurious effects which you can filter out using systematic behavior of the external magnetic field. I'm not going into the details of the analysis. You can find it in the various papers. So now what is orbital Hall effect? So orbital Hall effect, as I said, is very difficult to understand unless you get into all the theory of Berry curvature and all, but I will try as an experimentalist to explain you. So the idea is, if you have a multi-orbital materials like the transition metals, the Bloch states are momentum dependent superposition of the orbitals. For example, it could be a superposition of dxz and dxy because they are very close in energy. So this superposition, this complex superpositions, if you check dxz plus I dxy, if you look at its what is the Lz state, it will be plus h cross. But dxz minus I dxy will give you a minus h cross angular orbital angular momentum. So, and since these superpositions are momentum dependent, we have something called the orbital texture because it depends on the momentum as it progresses. So when you apply an electric field, your electron is evolving under the electric field, so there will be a Berry curvature. And it has been shown recently in 2018 that the Berry curvature, not only it is finite, it can be large, very, very large compared to the spin Berry curvature. So they have also given a fancy name, they call it orbital hotspot. Okay, and it's much, much larger than the spin Hall effect. So this is the calculation you can see here when they calculate the spin Hall effect and the orbital Hall effect. So even with materials where the spin orbit coupling is very low, say titanium, copper, niobium, molybdenum, chromium, the orbital Hall conductivity is much, much larger compared to spin Hall conductivity. And for reference, I have also given you large spin orbit coupling material, platinum and titanium. These are all theoretical calculation, and there are various. So after that theoretical paper, around 2020, various experiments started coming in. I have listed a few important one, and the last one is our paper. But I will highlight another paper here by Choi et al. That appeared in Nature. So there, instead of any electrical or anything, so they have directly measured the optical signal using again the Mock microscopy, just like the Oshpalom's paper. And they have indeed shown that there is accumulation of orbital angular momentum. Okay. Now coming back to this thickness. So why is thickness important? Because think about it. So suppose in the middle of this sample, a spin dependent scattering has happened. So upspin is going in a certain direction, but it will not go all the way as upspin up to the edge, because spin will relax. There is a lot of interaction going on. So only the part of the sample which is within the spin diffusion length, that accumulation will survive all the way to the edge. Rest will be lost. So even if you make something very thick, you will see that your effect has saturated. But what they shown for the orbital Hall effect, all the way up to 100 nanometer, the orbital Hall effect continues to increase. So that was another fantastic feature of this orbital Hall effect, is that it is long range compared to spin Hall effect, where the spin diffusion length is few nanometers, 3 to 4 at most. So that was another interest for studying the orbital Hall effect, because it is more robust than the spin Hall effect. So now, if I want to do the experiment that I have done for the spin torque, like the second harmonic experiment, I need one more ingredient, which is that the orbital Hall moment will directly not couple with the magnetization, because orbital and magnetization, they are different things. So what I need is another element that will convert the orbital to spin. Only then it will interact with the magnetization. So there are two approaches people have taken. Some experiments, they have introduced a very thin layer of a heavy metal between the orbital generating normal metal and the magnetization. But what we are doing is, we are choosing a ferromagnet which itself has a large spin orbit coupling. So as soon as the orbital enters the ferromagnet, it gets converted into spin. And this thing also has been theoretically studied, and it has been shown that iron and nickel, pure iron and pure nickel, they have opposite sign of this conversion. So it turns out that permalloy, commercially available permalloy, it has a right composition of iron and nickel, so that the overall orbital conversion is negligible. So permalloy acts as a control device. So if I say put permalloy with say niobium, I see that the signal is very less, because the orbitals to spin is not happening. But if I use pure nickel, then I immediately see a large signal. And that is how I establish that there is an orbital Hall effect, and whether it's not orbital Hall effect or spin Hall effect. So permalloy is the control. Okay. So here are some of our results here. So again, we see that we have varied the thickness up to 20 nanometer, and we see that the zeta parameter continues to increase. We have also varied the thickness of the ferromagnetic layer, because our idea was where the saturation happens in terms of conversion, and again it continues to increase. So this is something we do not understand. We are exploring more data. One problem that happens is that when you go to thicker and thicker sample, the resistance becomes so low that it becomes very difficult to generate high electric field, because your leads will start heating up if you pump in too much current. So that is one issue. So another thing that I wanted to talk about is that in addition, so far I talked about the Hall effect, that means XY. What happens in the XX? So it turns out even in the XX, because of all the things that I talked about, there is something called unidirectional magnetoresistance. So this is something similar to GMR. So if you have an interface like this, where you have a magnetization and you have a spin accumulation, so depending on the orientation of the magnetization, if the magnetization is in the other direction, the resistance level will change. So again you have a 0 and 1. So this is called unidirectional magnetoresistance, but it is in the XX channel. Okay, and the other thing is, another important thing is that now we are talking about the spin which is parallel or anti-parallel to the magnetization. So spin torque was transverse and this is parallel. So we have these two channels that we wanted to measure. So again we have measured Rxx as a function of phi. So this is a typical data. So just to summarize, so this is my experiment. So this is a setup very quickly. So this is our vector magnet. So what we are doing, we have a Hall bar, very small one, and we measure both xx and xy in the 2 omega channel as a function of phi. And we do a systematic measurements. So here I have plotted 5 different samples. I have nickel, chromium, molybdenum, copper, titanium and niobium. And I have plotted here on the x-axis is zeta E, the spin torque efficiency, and here it is the RUMR efficiency in the XX channel. And what we see is that there is a systematic dependence on each other. They are not independent, even though these are different materials. So again, this is something that we don't understand. We're asking the question whether there is any universal scaling behavior between RUMR and the zeta. So this is our first interesting result. And the second thing is regarding interface tuning. I will hurry up now. So again, this was seen in the context of spin torque, that if you introduced a small layer of copper between your normal metal and the heavy metal, that significantly enhances the spin torque efficiency. But it was very small amount. The copper thickness was like fraction of a nanometer. And the logic was, since copper is a D10 material, it's a fully filled D band, it will not allow hybridization to happen. So when you directly put, say, heavy metal in contact with a ferromagnet, there can be hybridization at the interface, and that leads to loss of spin. That's called the spin memory loss. So by introducing this copper thickness, they were able to show experimentally that indeed the spin torque efficiency increases. So we thought we'll try the same thing with our orbital, whether we can further enhance the orbital torque efficiency. So this is our result here. So let us follow the copper data, which is the blue curve. We have done the same thing for molybdenum. So when we introduce copper and look at the thickness, which is much, much larger, we see that there is a continuous increase in the efficiency. Particularly pay attention to the highest one, let's say the 10 nanometer. So for your reference, the dashed line here represents the zeta value for only copper nickel. And the first data point here with 0 thickness is directly titanium nickel. So what is the best case scenario? The best case scenario is that the orbital that is generated in copper and titanium, nothing happens to them. Both of them hit the nickel and they oscillate the nickel, right? So that is the best case scenario. But if you look at the value here, by introducing a 10 nanometer of copper, if you add this value and this value, the actual value is at least 2 to 3 times larger than what we expected. It means that the introduction of the copper layer has actually enhanced the orbital torque efficiency. Again, this is something that we do not understand, but we have also repeated the same thing with molybdenum. And both of them show the same trend, that putting a copper actually enhances the effect, not just add. And the last thing is, of course, temperature dependence. And this is related to the origin, like what is the origin of this effect, if we can understand. So just very quickly, so this is just to show you that there is nothing unusual in my sample. The dotted line here is the magnetization of the nickel. There is a 5% change, as we expect is a good metal. And the bilayer resistance, R by RT, they show a good metallic behavior. So no surprise here. But now let us look at the variation. Nickel, molybdenum, copper, titanium and niobium. All of them has one same trend, that up to around 200 Kelvin, there is a tendency to decrease. But copper is very distinct from all of them. It actually comes down very close to 0 continuously. Whereas molybdenum, after 200 Kelvin, it tends to increase. And then you have intermediate behavior in titanium and niobium. So now if you compare this with the spacer layer, the one that showed enhancement. So here I have plotted all three together. As you can see, the copper here tends to decrease. And this is the nickel titanium here, it's saturated at low temperature. But what happens to the one with the trilayer, with the thickness of around 10 nanometer? You see that copper actually suppresses the entire enhancement into almost zero. This is a log scale, by the way. So at room temperature, copper enhances the signal, enhance the torque efficiency, but at low temperature, it actually suppressed all the way to zero. So copper is something very special in terms of its behavior of the spin orbit coupling that requires more, needs to be looked at more. And so that is all I have to talk about today. So this is the summary. So we have talked about orbital to spin conversion efficiency of nickel. So the first important data is that even with increasing thickness of nickel, we don't see the saturation that we expected. Now we are not able to go to very high value further because of the problem of not able to maintain the device integrity, because if we can end up burning the sample. The second thing is, the second important result was that the orbital torque efficiency in different elements is directly proportional to the unidirectional magnetoresistance, the XX and XY channel. They seem to be follow a trending each other. They are not independent. And of course, the nature of the orbital Hall current is copper is very different from the other counterparts, titanium or molybdenum, even though they are in the same, in the periodic table, they are in the same band. And then the insertion of the orbital Hall effect enhanced the orbital torque efficiency, but at low temperature, it suppressed quite a bit. So that is what we talk about is the interface tuning. So using this copper interface, you can actually tune your net orbital torque efficiency. That is what we wanted to talk about. But of course, this requires more theoretical understanding. These are just results at the moment. We are doing more experiments on other materials also, and we are looking for theoretical support. That is where we stand. So thank you for your attention.
Questions, comments?
Can I?
Yeah, of course. All of you must be encouraged by him, Professor Datta Gupta. As he said, he was founder director of ISER Kolkata, and I will tell later on, if I have 1 minute, some other story about him.
Well, Partha, quite fascinating. You didn't have much time to talk about the relaxation phenomenon here, but as you mentioned, orbital relaxation. Now you're talking about actually a spintronic system because you have a spin-orbit coupling. So sigma gets coupled to the motion, which is there in the orbital angular momentum L, which is r cross p. And now when you talk about relaxation, it can occur both ways. It can occur in sigma as well as p, but most often it will be the p because the sigma relaxation is not so important. So p relaxation is like in Brownian motion. So especially in RXX, those effects would be, I think, quite important, right? The damping effects and the temperature dependence of that. Can you just comment on that?
No, we have measured both. I did not show it. We have measured both RXX and RXY as a function of temperature also. And they follow the trend. Like if RXY is decreasing, RXX is also decreasing.
Okay.
But one thing I will tell you, for orbital,
I'd like to know
the spin-orbit coupling is not important. That is the main thing. Even without spin-orbit coupling.
What happens probably is that, sorry, Dr. Professor Zaki-Rosen, can I just continue a little bit? So when you have a strong magnetic field, it will actually break the spin-orbit coupling. It's like the Paschen-Bach limit, I suppose. So that, it will couple the sigma, couple to L separately, and not to sigma plus L directly, and maybe that's the limit you're looking.
Okay, could be. But so one thing I will clarify, the role of the magnetic field here is only to rotate my magnetization, and it is very small. It is like 0.4 Tesla at most. That is the highest we give.
Professor Mitra, thank you so much for this fascinating data set. Well, I think apart from Professor Datta Gupta, what he mentioned, spintronics or orbitronics, possibly the domain that you are trying to explore.
Orbitronics, yeah.
Possibly. And
yeah.
Of course, I saw at least half dozen paper. They are trying to explain this fundamental of that keyword, orbitronics. But also I did not find something about whether as the spin reorientation lead to you anisotropy, whether are you expecting something like anisotropy driven by the orbital ordering, like anisotropy energy out of your orbital anisotropy. You got it right? I mean, what we have like spin anisotropy energy against orbital anisotropy associated energy. I mean, would you expect some kind of new domain in that direction? That anisotropy out of your orbital?
Yeah, that needs to be looked at. I don't have an immediate answer.
Since you and all are like titanium, molybdenum, all are closed cycles
Yes.
without
Yes.
any spin or any
Yes.
electron or
Yes.
anything else. So
Yes.
that would be fantastic domain to explore from Kolkata, I guess. Okay, thank you so much.
Any other?
Hello sir, thank you for a wonderful talk. Sir, I'm just curious to know and for the spin Hall conductivity, as you told we need to focus on the high atomic number material as offers the spin orbit coupling. So is there any way to choose to look at the high orbital Hall conductivity material?
So orbital Hall conductivity is reported, as I showed you, in all, like if you see the entire series, titanium all the way to ruthenium, they have shown orbital Hall effect.
Similar to spin Hall conductivity is a
Similar, spin Hall conductivity is restricted to right now platinum and tungsten and some work on tantalum.
Yes.
These are the three materials. Then of course there are topological insulators. I'm talking about only elements. For pure elements, spin Hall effect is restricted to tungsten and platinum and tantalum.
Okay.
But orbital Hall effect is almost everywhere. Every day there is a new data.
Okay.
And there are also work on things like copper oxide. There the orbital Hall effect is even much more. But since this is oxide, I did not talk about it.
Okay. Thank you, sir.
Yeah.
Okay, so if there are no more questions, let's thank him again. And the next